Dear students, welcome to the problem solving session on limit comparison test part 3. In the first session, we see basics on sequence and series, and then we solved few problems on part 1 and part 2 video. First watch that and come back to this session. In this session, we are going to see some interesting problems on limit comparison test. Let us recall the definition of limit comparison test. If we consider two positive term series, summation un and summation vn, then limit n tends to infinity un by vn should be some finite L and which is not equal to 0. If this condition satisfies, then summation un and summation vn either converge together or diverge together. Let us go into the session. Discuss the convergence of summation square root of n power 4 plus 1 minus square root of n power 4 minus 1. Now what is the difference between this problem and the previous session problems? All in our previous session we have some denominator so that we can tally the numerator and we can find Vn easily from the given problem. But now this problem does not contain any denominator. Suppose we are taking the problem as un. If we take n power 4 in common in each term, then we get square root of n power 4 into 1 plus 1 by n power 4 minus square root of n power 4 into 1 minus 1 by n power 4. And we know that square root of n power 4 is simply n square. Rewriting this, we get the un term like this. Now the problem is when I apply limit n tends to infinity, I will get infinity. According to limit comparison test, my limit n tends to infinity, the term un by vn should be L. It should not be equal to 0, and obviously there is one condition, it should not be equal to infinity because L should be finite. In all our previous problems, maybe we get sometime 0 or sometime non-zero. But in this problem, since we don't have any denominator, we can't tally this n square. It is a numerator. So when I apply limit n tends to infinity, my problem becomes infinity. Now my limit comparison test will get failed because my value should be finite and it should not be equal to 0. Here I get infinity. So we have to think how to tackle this problem in a wiser way. That's why I said this problem is little different. Now we want to rewrite the problem such that I should not get infinity. That means I need to do something such that I should not get terms in the numerator. My Vn should be something like 1 by n square or 1 by n cube, etc. I cannot take my Vn as n square. This is troubling me. Now let us consider the given problem. Nth term is un. To avoid this n square in the numerator, I am going to multiply and divide by the conjugate, that is square root of n power 4 plus 1 plus square root of n power 4 minus 1, and I am going to divide by the same. So now using our basic formula which we used in school, I can rewrite the problem in a very simpler way. Just to recall the formula, a plus b into a minus b is going to be a square minus b square. Here we have the terms with square root. So here we are going to rewrite the formula as root a minus root b into root a plus root b is equal to a minus b. And simplifying this, we will get only terms in the denominator which we consider as Vn. So square root of a minus square root of b into square root of a plus square root of b is going to be simply a minus b. So my numerator becomes simply n power 4 plus 1 minus n power 4 minus 1. I can cancel this n power 4. 1 minus of minus 1 is 2. So my numerator will become simply 2 and denominator I just get this term. Next we can take this n power 4 in common from each term and we will get like this. Now we know n power 4 root is n square. So I can rewrite this as n square into square root of 1 plus 1 by n power 4. Similarly, n square into square root of 1 minus 1 by n power 4 in the denominator. Next I can take this n square in common from both the terms and I get like this. Now we can see the numerator is 2 and denominator this term will become square root of 1 plus square root of 1 when you apply infinity. So it is going to be 2 and this is also not affect my problem. The only term which affect my problem is 1 by n square. So this 1 by n square is my trouble giving term. So let us consider my Vn as 1 by n square. Now Un by Vn I can easily tackle. Applying limit n tends to infinity, my numerator is 2, denominator is square root of 1 plus 0 plus square root of 1 minus 0. So we get 2 divided by root 1 plus root 1, that is 1 plus 1, simply 2 by 2. Therefore, I get 1, very important, this is not equal to 0. So now I can proceed further. The trouble giving term is 1 by n square. So let us take summation Vn is equal to summation 1 by n square. We have the standard result. Summation 1 by n power p converges if p greater than 1. Here our p value is 2. Obviously that is going to be greater than 1. So by this result we can declare summation 1 by n square is convergent. If summation 1 by n square is convergent, therefore summation Vn is convergence. And very important, by limit comparison test, if summation Vn converges, I can say summation un also converges. Therefore, the given series is a convergent series. Hope you understand. For more clarity, let us see one more problem on this kind. Discuss the convergence of summation square root of n plus 1 minus root n divided by n power p. You should not think that, okay, sir, this problem has denominator, so it is going to be normal. But this problem has a different issue. When I take the numerator, it has square root of n plus 1 minus root n. If I simplify, I'll try to take the n outside. We can rewrite this as square root of n into 1 plus 1 by n minus root n, that is root n into square root of 1 plus 1 by n minus root n. When you take root n in common, we have square root of 1 plus 1 by n minus 1. Now the nth term will be the numerator divided by n power p. That is okay. We can further simplify this by just seeing the power. The denominator we have p. Numerator we have n power 1 by 2. Root n by n power p, I can rewrite it as n power 1 by 2 divided by n power p. So it will be n power p into n power minus 1 by 2. So finally we can rewrite this as square root of 1 plus 1 by n minus 1 in the numerator. In the denominator, I can add the power since the base is same, n power p minus 1 by 2. And it is very obvious to see my denominator, which is my trouble giving term. So I can take this as Vn. Very important, Vn should be 1 by n power p minus 1 by 2. Even you take Vn, let us see what will happen to this problem. Now if you find Un by Vn, we get square root of 1 plus 1 by n minus 1. When we apply limit n tends to infinity on both sides, we get square root of 1 plus 0 minus 1, that is root 1 minus 1. Simply 1 minus 1, it is going to be 0. But according to the limit comparison test, when I apply limit n tends to infinity for un by vn, it should be some finite L and it should not be equal to 0. But we get 0 here. That means we should not think that limit comparison test is failed for this problem. But by rearranging the problem, we can solve the same problem using limit comparison test. So now we should be very careful when the problem has only numerator subtracted by two terms, because it may lead to 0 when you solve the problem directly by LCT. So what we have to do? We have to rearrange or simplify the problem using conjugate. So the only way is we have to multiply with the conjugate. Square root of n plus 1 plus square root of n. You have to multiply and divide so that we can easily tackle the problem. As usual, apply a square minus b square formula when we get a plus b into a minus b. So here we have root a minus root b into root a plus root b. That is going to be a minus b. Now both n will get cancelled. My numerator will become 1. Now we have to do simplification in the denominator. We have square root of n plus 1 plus square root of n. We have to take n in common. So n into 1 plus 1 by n. Here I can keep the root n as it is. Now if you take the root n in common, we get square root of 1 plus 1 by n plus 1. Now let us write the numerator and denominator. By taking this root n common, we have n power p into root n. That is nothing but n power p into n power 1 by 2. So we can rewrite this as n power p plus 1 by 2. So numerator is 1. It is not going to affect the problem. And then when we go to the denominator, we have two terms. When we apply limit n tends to infinity, we get 1 plus 0 plus 1. So root 1 is 1. 1 plus 1 is going to be 2. So this will not affect the problem. The trouble giving term is n power p plus 1 by 2. Now we have to find un by vn. Just neglect this term and write the remaining data. That is my un by vn. Now when you apply limit n tends to infinity, we get 1 by square root of 1 plus 1, that is 1 by 2, and very important, it is not equal to 0. Therefore the condition satisfies. Now let us deal with the trouble giving term. Summation vn is equal to summation 1 by n power p plus 1 by 2. We know this result. Summation 1 by n power p converges if p greater than 1. So here we have p plus 1 by 2. So we have to say when p plus 1 by 2 greater than 1, then summation vn converges. Simplifying this, we get p greater than 1 minus 1 by 2, that is simply p greater than 1 by 2. So in this problem, it is special. When p greater than 1 by 2, summation vn converges. If p less than or equal to 1 by 2, then summation vn diverges. So we have to write it very clearly. Then by limit comparison test, summation un converge when p is greater than 1 by 2, and summation vn is divergent when p is less than or equal to 1 by 2. Hope you understand, students.
Thanks for watching. Subscribe to our channel and share to your friends. See you in the next video. Bye bye.